All right, section 5 is going to deal with hybrid orbitals, and this is something completely new for us. The VSEPR model predicts molecular shape well, despite the fact that it has no relationship to the filling and shapes of atomic orbitals, so nothing to do with the SP, D, and F at all. We reconcile the notion that covalent bonds are formed from the overlap of atomic orbitals that we just looked at in the previous section, and we use this process called hybridization. It explains the geometries we assume that atomic orbitals on the atom mix to form new orbitals that we call hybrid orbitals. So we're going to be mixing SPs and Ds to give us these different kinds of hybrid orbitals. Okay, these shapes of these hybrid orbitals are different from the original, but the total number of orbitals is constant. Okay, so the hybrid number that we have orbital-wise is equal to the orbitals that are mixed together. So if you mix 3 orbitals together, you're going to have 3 hybrid orbitals when you're done. And again, these mixing just reconciles this idea of the VSEPR model and how these shapes are taken, but still within the bonds being formed by orbitals overlapping. So let's look at an example. We're going to start off with BeF2. We're going to draw the Lewis structure for BeF2, and then we're going to look at the bonding. Okay, BeF2, we have beryllium in the middle, 2 fluorines. Okay, all the fluorines have the little electrons around the outside. So we should have 2 identical bonds, 1 to each fluorine. So we're going to look at the bonding for each thing. The bonding for F and the bonding for Be, and we're going to explain these hybrid orbitals. Okay, so if we look at the electron notation or orbital diagrams for F, okay, we have 1s2, 2s2, 2p5. So we look at these valence electrons, we're mostly dealing with the p's here because those are the ones that are on the outer that are going to overlap with the beryllium. So if I look at the fluorines 2p's, there are 5 there. If I look at the beryllium is 1s2, 2s2, so it's going to overlap its 2 s's with fluorines 2p's. So these 2 bonds need to look exactly the same and have exactly the same type of orbitals. So what happens is one of these is going to pair with a beryllium. But notice how these are not unpaired. Well, in order to form 2 identical bonds, I need to have something that is going to have kind of like a lone electron to then bond with one of the fluorines. Because this fluorine is good, it's got an open space here that it can have another electron in to share with beryllium, but beryllium does not. So what happens is one of these electrons here in beryllium gets kind of promoted, and we've got these 2p's. Remember, 2p's are always in 3's. So it gets promoted here, and now I've got a 2s and a 2p, and each one is by itself. Okay, so now one fluorine could bond here, and another fluorine could bond here. The problem is those are not the actual same type. So we're going to look at what allows these bonds to form. Okay, your 2s orbital mixes with the 2p orbital to form 2 identical hybridized orbitals. So it forms 2 identical what we call sp orbitals for beryllium. An s and a p mix, and we get what's called an sp. Okay, now beryllium then is going to be ready to bond. So if we look at this picture here, we take the s orbital and a p orbital and we mix them. So beryllium now is going to look like this with a 2sp. We've still got these extra 2p's that didn't get used. You took one s and one p, smushed them together, and now you've got an sp orbital. And these ones in my purple here are the hybridized sp orbitals. Notice how they are kind of circular and kind of lobe-shaped when they get hybridized together. So you've got 2 identical orbitals, which is what you want. Okay? So what we do now is we're going to show how these bond together. So I've got beryllium, which is going to have the 1s with its electrons, and then it's got 2 sps, okay, that I just hybridized. A fluorine's going to come along and it's got its 2s and 2 p's. And its 2p here is free, so this p orbital is going to now bond here with this beryllium for one bond. Another fluorine is going to come along, look the exact same like this one does, and bond right here. And now I'm going to have two identical sp bonds. So that is the easiest type of hybrid orbital, that is with an sp hybrid orbital. Let's look at one a little bit harder, which is the sp2 and the sp3. Okay, sp2 and sp3 are when atomic orbitals are mixed. They again have the same number produced as they are that went into them. Okay, so 3 sp2 hybrid orbitals lie in the same plane and are 120 degrees apart from one another. They are used to form 3 equivalent bonds with 3 fluorine atoms in BF3. And there's still going to be one unfilled 2p that we're going to look at here in a second. So if you look at BF3, we've got boron and 3 fluorines. So we're going to have 3 identical bonds is what we need. So what happens is we look at boron. Boron is 1s2, 2s2, 2p1. And fluorine is the same as before with the 1s2, 2s2, 2p5. So boron only has one p open, and it needs to form 3 identical bonds. So what happens is we take borons, okay, boron is 2s2, 2p1. So we're going to have 2s with 2s and 2p with 1. This s here is going to get promoted up to one of these p's, but what happens is then we hybridize these 3, and we call all 3 of those sp2, and you've got 3 of them. And I've still got one lone little one lone little p that does not get used. But now I've got 3 identical sp2 bonds, and those are what I have in the purple there. So now boron can form 3 identical bonds. If we look at sp3, okay, we're going to look at the example of CH4. So I've got carbon, and it needs to form 4 identical bonds. So this time we're going to use 1s and all 3 p's. Okay, if I look at carbon, carbon is 1s2, 2s2, 2p2. I need 4 identical bonds where I've got 4 valence electrons here. So an s up, down, my p up, up. And hydrogen, of course, only has, 1 electron, so it's good to go to form its 1 bond each time. So what happens is now this s gets promoted in the carbon. We take all 4 of these, and we're going to make 4 identical bonds. 4 go in, 4 come out. We've got sp3, 4 identical electrons that now can each can now bond with each one of these. So each one of those spots is now like a bonding spot with each particular hydrogen. And notice again, you've got 1s and 3 p's that then goes into sitting here with 4 identical bonds around your center. Okay, this idea can also be used to describe bonding in atoms that have lone pairs, as they still have the same basic geometry as their atom counterparts. Okay, here we have an example where we have 2 hybrid orbitals that contain non-bonding pairs or lone pairs, while the other 2 are used to form bonds. Now you've still got 4 identical bonds. Just 2 are lone pairs, 2 are atoms. Now my example here is water. So when we talked about those electron domain geometries being the overarching one, that's all you really care about. How many things are around your center? If there are 4, you will always have an sp3 hybrid orbitals that need to be used, whether they are with lone pairs or whether they are with atoms. All right, hybridization involving d orbitals. Okay, except H and He, all atoms have 1s and 3 p's. Okay, that leaves a maximum number of 4 for the hybrid orbitals. Now, if you want to look at where you have bonds that are more than 4, that's where we're looking at atoms that use your d orbitals, as they have the same energy level number. Okay, you can have sp, I'm not going to do this very well, but that should be a superscript 3D. Those are the trigonal bipyramidal. That way we have 5 bonds, and you've got sp3d2, and again that 2 and the 3 should be superscript. Those are the octahedral, and those are where you have 6 bonds. And these are our expanded octets. So notice here how we have 1 s, 3 p's, and a d for 5. You add 1 more d, you've got 6. We do not do anything more than 6. Okay, hybrid orbital summary then, if you flip over, you got to have a big chart there. They are a convenient way to use the valence bond theory, talking about bond overlap. You need to draw your Lewis structure, look at your molecular geometry, and specify which hybrid orbitals you're going to use. We don't do anything more than looking at drawing orbital diagrams as to how the electrons make these hybrid orbitals, and then specifying what type of hybrid orbital each kind of molecule has. You do have this chart. You got some examples there with linear, trigonal, planar, tetrahedral, and you've got the sp, sp2, sp3, sp3d, and sp3d2. So let's look at the examples and then we're done. Okay, it says indicate the hybridization of orbitals employed by the central atom. So I've got NH2 minus. Okay, I've got N and 2 H's, and that's all I need beside my lone pairs. Now I've got 4 things around my center, which is really tetrahedral. Since there are 4 things there, that means I am looking at sp3 as my type of hybrid orbitals that are going to get used. If I now flip and look at sf4, be careful with your total electron number here. You are going to need some lone pairs on sulfur, and you're going to need 1 set of lone pairs. This is trigonal bipyramidal. So you are now looking at 5 things around your center, which is an sp3d. You cannot have a higher number in the p orbital than 3 because you don't have more than 3 p orbitals available to use.